Hello there, and welcome to Science with Sleepy. If you love discovering how we're peering back 13 billion years to see the universe's first light, or learning about exoplanets with diamond clouds and soot-filled skies, you're going to want to subscribe. Because tonight, we're exploring the most powerful telescope ever built, the James Webb Space Telescope, a machine that's already rewritten our understanding of cosmic history. And it's just getting started. Imagine seeing the first stars, the very first stars that ever formed in the universe, stars that burned bright billions of years ago. Stars that died long before our sun was born. Stars that created the elements making up everything around you, everything you're made of. But there's a problem. Those stars are so far away, so faint, so ancient that no telescope has ever been able to see them, until now, until the James Webb Space Telescope. Imagine this. You want to see the first stars, the very first stars that ever formed in the universe, stars that burned bright billions of years ago. Stars that died long before our sun was born, stars that created the elements that make up everything around you, everything you're made of. But there's a problem. Those stars are so far away, so faint, so ancient, that no telescope has ever been able to see them. Until now. Until the James Webb Space Telescope. The James Webb Space Telescope is unlike any telescope that came before it. It's bigger, it's more powerful, it sees in ways we've never seen before. Already, it's revealing galaxies that formed just 280 million years after the Big Bang. It's showing us exoplanets with atmospheres we never knew existed. It's capturing the birth of stars in incredible detail, and it's rewriting our understanding of cosmic history. Tonight we'll explore how Webb came to be. From a dream in the 1990s to a reality floating in space. We'll discover the engineering marvels that make Webb possible. The golden mirror. The sunshield the size of a tennis court. The incredible precision that lets it see billions of light-years away. We'll witness Webb's stunning discoveries. The most distant galaxy ever seen. The most distant supernova ever observed. Exoplanets with diamond clouds and soot-filled atmospheres. Black holes from the universe's infancy. Galaxies that shouldn't exist but do. This is a story about human curiosity, about our drive to explore, about our need to understand where we came from and where we're going. Chapter 1: The Dream and the Journey. The story of the James Webb Space Telescope begins with a question, a simple question. What if we could see the first stars? What if we could look back in time to the universe's earliest moments? What if we could watch galaxies form, see stars being born, discover planets around other suns? These questions haunted astronomers for decades. They knew the answers were out there, written in light, traveling through space, waiting to be seen. But they needed a telescope powerful enough to see them, a telescope that could peer deeper into space than ever before. A telescope that could see the universe's first light. The idea for what would become the James Webb Space Telescope started in the 1990s. Scientists were already dreaming big. The Hubble Space Telescope had just launched. It was showing us the universe in ways we'd never seen before. But Hubble had limits. It could see far, but not far enough. It could see galaxies, but not the first galaxies. It could see stars, but not the first stars. Hubble's mirror was 2.4 meters across. That was huge for its time. But astronomers knew they needed something bigger. Something that could see in infrared light. Something that could peer deeper into the cosmos. So astronomers began to dream. What if we built a telescope even bigger than Hubble? What if we made it see in infrared light? What if we put it far from Earth, where it could stay cold, where it could see without interference? What if we built a telescope that could see the universe's first light? The idea was ambitious. Almost impossibly ambitious. It would require technology that didn't exist yet, engineering solutions that had never been tried, a budget that would make governments nervous. But the dream was too powerful to ignore. The project was originally called the Next Generation Space Telescope. Later, it would be renamed the James Webb Space Telescope, after James E. Webb, the NASA administrator who led the agency during the Apollo program, the man who helped put humans on the moon. But the journey from idea to reality would be long, very long, longer than anyone expected. The project would face delays, budget overruns, technical challenges that seemed impossible to solve. There were times when it seemed like the telescope would never be built, times when it seemed like the dream was too big. The original plan called for the telescope to launch in 2007, but 2007 came and went. The telescope wasn't ready. It wasn't even close to ready. The budget kept growing, from $500 million to $1 billion, to $2 billion, to $10 billion. According to NASA's own reports, the project faced over 300 technical challenges that needed solving. Each one tested the limits of engineering. Each one required new solutions. The delays kept coming, technical problems kept appearing, solutions kept being found. But slowly, very slowly. There were moments when the project almost died. In 2011, Congress threatened to cancel it. The budget had grown too large. The delays had lasted too long. But scientists fought back. They explained why Webb mattered, why it was worth the cost, why it was worth the wait. And Congress listened. The project survived. The fight to save Webb was intense. Scientists wrote letters, made phone calls, testified before Congress, explained why Webb was essential, why it couldn't be cancelled, why it had to be built. They argued that Webb would answer fundamental questions about how the universe began, about how galaxies formed, about how stars were born, about whether life exists beyond Earth. These questions were worth answering. These discoveries were worth making. And Congress agreed. The project was saved. But with conditions. The budget was capped. The timeline was tightened. The pressure increased. But the scientists and engineers rose to the challenge. They found ways to save money, to work faster, to make it happen. The project continued, slowly, carefully, but it continued. And eventually, Webb was built, launched, deployed, and it's working perfectly. The fight was worth it, the struggle was worth it, the dream became reality. But the challenges didn't end there. Building Webb was like building a Swiss watch. But a Swiss watch the size of a tennis court. That had to work perfectly. In the vacuum of space. At temperatures colder than anything on Earth. With no chance for repairs. No chance for fixes. It had to work perfectly the first time. Because there would be no second chance. The telescope's mirror would be made of 18 hexagonal segments. Each one had to be perfect. Each one had to be aligned with the others. To within a fraction of the width of a human hair, engineers calculated that the alignment precision needed to be within 50 nanometers. That's about 1/10,000th the width of a human hair. The sunshield would be the size of a tennis court, made of 5 layers, each one thinner than a human hair. It had to unfold perfectly, in space, with no one there to fix it if something went wrong. The deployment sequence had 344 single points of failure. 344 things that could go wrong. 344 things that had to work perfectly. If any one of them failed, the entire mission could fail. The entire $10 billion investment could be lost. NASA engineers documented every single one of these potential failures. They tested each component over and over. They simulated the entire deployment sequence hundreds of times. They built full-scale test models. They tested in vacuum chambers. They tested at extreme temperatures. They tested everything until they were confident that every single component would work, that every single step would succeed, that the mission would not fail. But the engineers kept working. They tested everything over and over. They simulated the deployment hundreds of times. They built test models. They broke things. They fixed them. They learned. They improved. They made it work. The telescope was built by NASA, but it wasn't built alone. The European Space Agency, or ESA, provided the launch vehicle, the Ariane 5 rocket. One of the most reliable rockets ever built. The Canadian Space Agency, or CSA, provided one of the telescope's instruments, the Fine Guidance Sensor. The instrument that helps Webb point precisely at its targets. It was an international effort, scientists and engineers from around the world working together for decades to build something that had never been built before, something that would change how we see the universe. Finally, after more than 30 years of planning and building, the day arrived, December 25, 2021, Christmas Day. The James Webb Space Telescope sat on top of an Ariane 5 rocket in French Guiana, on the edge of the Atlantic Ocean, ready to launch. The rocket ignited. The flames roared, the ground shook, and Webb began its journey up through the atmosphere, into space, away from Earth, toward its destination, a point in space called L2, 1.5 million kilometers from Earth, where it would spend the next decade or more, observing the universe. But the journey wasn't over. Not yet. Webb had to unfold. It had been folded up like origami to fit inside the rocket. Now, it had to unfold perfectly in space, with no one there to help. The deployment sequence would take weeks. First, the solar panels unfolded, then the sunshield, layer by layer, each one critical, each one tested thousands of times. But never in space, never for real, until now. The sunshield deployment was the most complex part, 5 layers, each one the size of a tennis court. Each one had to unfold perfectly. If one layer touched another, the mission could fail. If one layer tore, the mission could fail. If anything went wrong, there was no way to fix it. But it worked perfectly. The sunshield unfolded, the layers separated. The telescope was protected from the sun's heat. It could begin to cool down, to reach the incredibly cold temperatures it needed to see infrared light. Then came the mirror, 18 hexagonal segments. Each one had to unfold, each one had to align, to within nanometers. A nanometer is 1/1000th of a meter. That's how precise the alignment had to be. That's how perfect everything had to be. And it was. The mirror unfolded, the segments aligned, the telescope was ready. Almost. It still had to cool down, to reach its operating temperature. -447 degrees Fahrenheit. Colder than liquid nitrogen. Colder than almost anything in the universe. It took months. But finally, Webb was ready. Ready to see the universe. Ready to reveal its secrets. Ready to rewrite everything we thought we knew. The first images arrived in July 2022. 6 months after launch. They were stunning. More beautiful than anyone had imagined. More detailed than anyone had hoped. They showed galaxies. Thousands of them. In a patch of sky smaller than a grain of sand held at arm's length. NASA calculated that this tiny patch of sky represents less than 1/1,000,000th of the total sky. Yet it contained thousands of galaxies, each one a collection of billions of stars. If you extrapolated this density across the entire sky, astronomers estimate there could be hundreds of billions of galaxies in the observable universe. Maybe even trillions. That's how vast the cosmos really is. The release of the first images was a global event. Millions of people watched, waited, anticipated. What would Webb show? What would it reveal? What would we see? When the images finally arrived, they exceeded all expectations. They were more beautiful than anyone had imagined. More detailed than anyone had hoped. They showed galaxies, stars, nebulae, in incredible detail, in colors we'd never seen before. The first deep field image was particularly stunning. It showed thousands of galaxies in a tiny patch of sky, each one a collection of billions of stars, each one a universe in itself, and some of them were incredibly distant, incredibly old, formed when the universe was young. People around the world were amazed, inspired, moved. The images were shared everywhere, on social media, in news articles, in classrooms. They became symbols. Symbols of human achievement, symbols of exploration, symbols of wonder. But the images were more than just beautiful, they were scientific. They revealed new information about the early universe, about galaxy formation, about cosmic history. They answered questions, raised new questions, started new research, began new discoveries. But these weren't just any galaxies. These were some of the earliest galaxies ever seen. Galaxies that formed billions of years ago, when the universe was young, when stars were first being born, when everything was just beginning. Each galaxy in that image tells a story of formation, of evolution, of cosmic history. Some are spiral galaxies, like our Milky Way, with beautiful arms, full of stars. Others are elliptical galaxies, round, smooth, older. Some are irregular, chaotic, still forming. Each one is unique. Each one is beautiful, each one is a universe in itself. But the most exciting galaxies are the faintest ones, the ones that are barely visible, the ones that are incredibly distant, the ones that formed when the universe was young. These are the galaxies Webb was built to see. The galaxies that hold the secrets to how everything began, to how galaxies formed, to how the universe evolved. The first deep field image was just the beginning. Since then, Webb has taken many more deep field images, each one revealing more galaxies, each one going deeper, each one seeing farther back in time. The discoveries keep coming. The mysteries keep being revealed. The universe keeps surprising us. The journey was complete. The dream was real. The James Webb Space Telescope was working. And it was already changing everything. But this was just the beginning. The telescope had decades of observations ahead of it, decades of discoveries waiting to be made. The journey from idea to reality had taken more than 30 years. But the journey of discovery was just starting. The story of Webb's development is a story of persistence, of determination, of refusing to give up, even when things seemed impossible, even when budgets grew, even when deadlines slipped. The scientists and engineers kept working, kept solving problems, kept moving forward. There were countless challenges along the way. Technical problems that seemed unsolvable. Budget crises that threatened to end the project. Delays that tested everyone's patience. But through it all, the vision remained. The dream stayed alive, the determination never wavered. And now, Webb is in space, working perfectly, making discoveries, rewriting our understanding of the universe. The 30-year journey was worth it. Every delay, every challenge, every moment of doubt. Because now we can see the universe's first light. We can explore its deepest secrets. We can answer questions we've been asking for centuries. The James Webb Space Telescope is more than just a telescope. It's a testament to human curiosity, to our drive to explore, to our need to understand. It's proof that when we dream big, when we work together, when we refuse to give up, we can achieve the impossible. Chapter 2: The Engineering Marvel. The James Webb Space Telescope is an engineering marvel. There's no other way to describe it. It's like nothing that's ever been built before. Every part of it pushes the limits of what's possible. Every component is designed to perfection. Every system works together to create something extraordinary. Let's start with the mirror. Webb's primary mirror is huge, 6.5 meters across. That's about 21 feet. More than 2.5 times bigger than Hubble's mirror. But size isn't everything. The mirror also has to be perfect. Or as close to perfect as humans can make it. The mirror is made of beryllium, a lightweight metal, stronger than steel, but lighter than aluminum, perfect for space, where every kilogram costs thousands of dollars to launch. But beryllium isn't easy to work with. It's toxic, it's brittle, it's difficult to shape. Engineers had to develop special techniques just to work with it. They wore protective suits, used special tools, created new methods, all to shape this perfect material. For the perfect mirror. The mirror isn't one piece, it's 18 pieces, 18 hexagonal segments. Each one is a perfect hexagon, about 4.5 feet across. Each one weighs about 88 pounds. But here's the thing. Each segment had to be shaped perfectly, to within nanometers. A nanometer is 1/1000th of a meter. That's incredibly precise. That's incredibly difficult. According to NASA's engineering reports, each segment was polished to a surface accuracy of 20 nanometers. That means if you scaled one segment to the size of the United States, any bumps or imperfections would be less than 2 inches high. That's how smooth these mirrors had to be. But shaping the mirror was just the beginning. Each segment had to be coated with gold. Yes, gold. The mirror is covered in a thin layer of gold, about 100 nanometers thick. That's about 1,000 times thinner than a human hair. But why gold? Gold is special. It reflects infrared light better than almost any other material. And Webb sees in infrared light. That's how it can see the earliest galaxies, the first stars, the birth of planets. Infrared light has longer wavelengths than visible light. It can pass through dust clouds. It can reveal things hidden from other telescopes. But gold isn't easy to apply. The coating had to be perfect. Any imperfections would scatter light, would reduce the telescope's ability to see faint objects, would limit its discoveries. So engineers developed a special technique. They vaporized the gold, turned it into a gas, then let it settle onto the mirror segments, creating a perfect coating, a perfect surface for reflecting infrared light. But the mirror isn't just gold. It's also covered in a protective layer, silicon dioxide. To protect the gold, to keep it from degrading, to ensure it lasts for decades in space, the mirror segments had to be aligned perfectly, to within nanometers. That's incredibly precise. Imagine trying to align 18 mirrors, each one the size of a small car, to within a fraction of the width of a human hair, from 1,000,000 miles away, with no one there to adjust them. But Webb can adjust itself. Each mirror segment has 7 actuators, small motors, that can move the segment up, down, left, right, tilt it, adjust its shape, all controlled from Earth, all working together to create one perfect mirror. The alignment process took months. Engineers would take images, analyze them, adjust the mirrors, take more images, analyze again, adjust again, over and over, until the 18 segments became one perfect mirror, one perfect eye on the universe. The process was painstaking. Each adjustment was tiny, measured in nanometers. But each one mattered. Each one brought the segments closer together. Each one improved the image quality. Engineers used a technique called phase retrieval. They would take images of a bright star, analyze the light patterns, determine how the mirrors were misaligned, then adjust them, slightly, precisely, then take more images, analyze again, adjust again. The process repeated, hundreds of times, thousands of times, until the 18 segments worked as one, until the image was perfect, until Webb could see clearly. It was a test of patience, of precision, of determination. But it worked. The mirrors aligned, the telescope focused, Webb could see, and it could see clearly. More clearly than any telescope before it. But the mirror is just one part of Webb, the sunshield is another, and it's just as impressive. The sunshield is huge, the size of a tennis court. About 70 feet by 47 feet, but it's incredibly thin. Each layer is thinner than a human hair, made of a special material called kapton. Coated with aluminum and silicon, NASA engineers calculated that each layer is only 0.00005 inches thick. That's about 1/5 the thickness of a human hair. Yet these 5 layers together can reduce the sun's heat by a factor of over 1,000,000. The top layer faces the sun at 185 degrees Fahrenheit. The bottom layer, facing the telescope, stays at -388 degrees Fahrenheit. That's a temperature difference of over 570 degrees. Across just 5 thin layers. The sunshield has 5 layers, 5 separate sheets, each one slightly smaller than the one below it, creating a tent-like structure. That blocks the sun's heat, that keeps the telescope cold, that allows it to see infrared light. Here's why this matters. Everything gives off heat. Everything emits infrared light. Even the telescope itself, even the instruments, even the electronics. But to see faint infrared light from distant galaxies, Webb has to be incredibly cold, colder than almost anything in the universe. The sunshield blocks sunlight, reflects it away, keeps the telescope in shadow, allows it to cool down, to reach its operating temperature. -447 degrees Fahrenheit. That's incredibly cold, colder than liquid nitrogen, colder than the surface of Pluto, almost as cold as space itself. But the sunshield had to unfold, perfectly, in space, with no one there to help. It was folded up, like origami, to fit inside the rocket. Then, it had to unfold. Each layer, each sheet, each part, had to work perfectly. Because if it didn't, the mission would fail. The deployment was one of the most complex operations ever attempted in space. The sunshield had to unfold. The layers had to separate, they couldn't touch each other. They couldn't tear, they couldn't get stuck. Everything had to work perfectly. The first time. Because there would be no second chance. And it did. The sunshield unfolded. Perfectly. The layers separated. The telescope began to cool. To reach the incredibly cold temperatures it needed. To see the universe's first light. The sunshield deployment was watched by millions of people around the world. Live streams showed the process. Step by step. Layer by layer. Everyone held their breath. Waiting. Hoping. That everything would work. that the years of planning would pay off, that the dream would become reality. But Webb's location is just as important as its sunshield. Webb orbits at a special point in space, called L2, the second Lagrange point, named after Joseph Louis Lagrange, an 18th-century mathematician who discovered these special points, where gravitational forces balance out. L2 is located about 1.5 million kilometers from Earth, 4 times farther than the Moon. But it's worth the distance. Because at L2, Webb can stay in a stable orbit, with minimal fuel, can observe continuously, without Earth blocking its view, can stay cold, because it's always in Earth's shadow, protected from the sun's heat. L2 is like a parking spot in space, a place where objects can stay, without drifting, without moving, perfect for a telescope that needs to observe for years, that needs to stay pointed, that needs to stay cold. Getting to L2 took about a month. After launch, Webb had to travel there, settle into its orbit, begin its mission. But once there, it was perfect, the perfect location, for the perfect telescope. And it did. Each layer unfolded perfectly. The tension was released. The relief was palpable. The sunshield was working. The telescope was protected. The mission could continue. But keeping Webb cold isn't just about the sunshield. The telescope also has a cryocooler, a special cooling system that keeps the instruments even colder. The mid-infrared instrument, or MIRI, has to be even colder than the rest of the telescope. -447 degrees Fahrenheit. That's incredibly cold, almost absolute zero. The cryocooler is a marvel of engineering. It uses helium, liquid helium, to cool the instruments. But helium is tricky. It's a gas at room temperature. It has to be cooled, compressed, turned into a liquid, then used to cool the instruments, all while floating in space, 1,000,000 miles from Earth, with no one there to fix it if something goes wrong. The cryocooler works like a refrigerator, but in reverse. Instead of keeping things warm, it keeps things cold, incredibly cold. It uses a process called the Joule-Thomson effect, where a gas cools when it expands. The cryocooler compresses helium, then lets it expand, over and over, creating a cycle. That removes heat, that cools the instruments, that keeps them at the perfect temperature. Engineers spent years perfecting this system. They had to ensure it would work in zero gravity, with no convection to help move heat. They had to make it reliable, because if it failed, MIRI would stop working, and we'd lose one of Webb's most powerful instruments. But it works perfectly, keeping MIRI at -447 degrees Fahrenheit, allowing it to see mid-infrared light, revealing objects invisible to other telescopes. But the cryocooler had to be tested extensively on Earth, in space-like conditions, to make sure it would work in space, 1,000,000 miles away, with no repairs possible. The tests were rigorous, the standards were high, the pressure was intense. But it worked. The cryocooler works perfectly, keeping MIRI at the perfect temperature, allowing it to see mid-infrared light, revealing objects invisible to other instruments. The cryocooler is a complex system. It uses helium, liquid helium, to cool the instruments, to keep them at the perfect temperature, to allow them to see infrared light, without interference, without noise, without anything that would block the faint signals from distant galaxies. But Webb isn't just about being cold, it's also about being precise. Incredibly precise. The telescope has to point at its targets with incredible accuracy. It has to hold that position for hours, sometimes days, while it collects light, from objects billions of light-years away. Webb's pointing accuracy is incredible. It can point at a target and hold that position to within a fraction of an arcsecond. An arcsecond is a tiny angle. Imagine holding a laser pointer from a mile away and keeping it pointed at a target the size of a coin. That's how precise Webb's pointing is. According to NASA's specifications, Webb can point with an accuracy of 0.007 arcseconds. That's like being able to see a penny from 24 miles away and hold that view steady for hours, sometimes days, while collecting light from objects billions of light-years away. This precision comes from the fine guidance sensor built by the Canadian Space Agency. It uses guide stars, bright stars near the target, to help Webb point precisely, to keep it locked on, to ensure it doesn't drift, even slightly. But precision isn't just about pointing, it's also about stability. Webb has to be stable, incredibly stable. It can't vibrate, it can't shake, it can't move, even slightly, because any movement would blur the images, would reduce the telescope's ability to see faint objects, would limit its discoveries. So Webb is built to be stable. The mirror segments are rigid, the structure is strong, the instruments are isolated from vibrations, from movement, from anything that could disturb the observations. But Webb isn't just about the hardware, it's also about the software, the computer programs that control everything, that process the data, that make the discoveries possible. Webb software is complex, millions of lines of code, controlling every aspect of the telescope, from pointing to focusing, to taking images, to processing data. Everything is controlled by software, everything is automated, everything works together to create something extraordinary. The telescope has 4 main science instruments, each one designed for a specific purpose, each one capable of incredible discoveries. NIRCam is the near-infrared camera. It takes images. In near-infrared light, it can see galaxies, stars, planets, in incredible detail. It was used to align the mirror segments, to create the first stunning images, to discover the most distant galaxies. NIR-SPEC is the near-infrared spectrograph. It doesn't just take images, it analyzes light, breaks it into its component colors, reveals what things are made of, how fast they're moving, how far away they are. It can observe hundreds of objects at once, using microshutters, tiny doors that open and close, to select which objects to study. NIR-SPEC has 248,000 individual microshutters. Each one is smaller than a human hair. Each one can be opened or closed independently. This allows astronomers to study up to 100 objects simultaneously in a single observation. It's like having 100 telescopes, all pointing at different targets, all at the same time. MIRI is the mid-infrared instrument. It sees in mid-infrared light, longer wavelengths, that reveal cooler objects, dust clouds, planet-forming disks, the building blocks of planets. It has to be incredibly cold to see these faint signals, to reveal these hidden objects. FGS is the fine guidance sensor. It helps Webb point precisely, but it can also take images, scientific images, while helping the telescope stay on target. Each instrument is a masterpiece of engineering, of science, of human ingenuity. They work together, complementing each other, revealing different aspects of the universe, creating a complete picture of everything Webb observes. But the instruments aren't just tools. They're extensions of human curiosity, of our desire to explore, of our need to understand. They're our eyes, in the darkness of space, our ears, listening to the whispers of the cosmos, our hands, reaching out to touch the universe's deepest secrets. All of these instruments work together to create a complete picture of the universe, to reveal its secrets, to answer questions we've been asking for centuries. They're the heart of Webb, the reason it exists, the tools that make discovery possible. But building Webb wasn't just about the technology, it was also about the people. Thousands of people, from around the world, working together, for decades, to make the dream real. Engineers, scientists, technicians, managers, all working together, all contributing, all making Webb possible. Some of these people spent their entire careers on Webb, started working on it as young engineers, retired after seeing it launch. Their whole professional lives dedicated to one project, one dream, one telescope. Others joined the project along the way, brought new ideas, new skills, new perspectives, helped solve problems, helped overcome challenges, helped make Webb real. And then there were the students, the interns, the young scientists, who worked on Webb, who learned from it, who will carry its legacy forward, who will build the next generation of telescopes, who will make the next discoveries. The James Webb Space Telescope is an engineering marvel, there's no doubt about it. It pushes the limits of what's possible. It demonstrates what humans can achieve when we dream big, when we work together, when we refuse to give up. But the engineering is just the beginning. The real marvel is what Webb can see, what it can discover, what it can teach us about the universe. And that's what we'll explore next. Every component of Webb had to be perfect. Every system had to work flawlessly. Every detail mattered, because Webb is 1,000,000 miles away, too far for repairs, too far for fixes. It had to work perfectly, the first time, and it does. The precision is incredible, the engineering is flawless, the telescope is a masterpiece. A testament to human ingenuity, a symbol of what we can achieve when we set our minds to it, when we refuse to give up, when we dream big. Chapter 3: Seeing the First Light. Light is a time machine. Think about that for a moment. When you look at the sun, you're seeing it as it was 8 minutes ago. That's how long it takes light to travel from the sun to Earth, 8 minutes. So you're always looking into the past, always seeing things as they were, not as they are. But the sun is close, very close, just 8 light minutes away. What about stars that are farther away? What about galaxies? What about the earliest galaxies, the ones that formed billions of years ago? Can we see those? The answer is yes, but only if we have a telescope powerful enough, a telescope that can see incredibly faint light. Light that's been traveling through space for billions of years, light from the universe's earliest moments. That's what the James Webb Space Telescope does. It sees the first light, the light from the first stars, the first galaxies, the universe's earliest moments. It's like looking back in time, to when everything was just beginning. Here's how it works. Light travels at a constant speed, about 186,000 miles per second. Incredibly fast, but space is incredibly vast. So even at that speed, light takes time to travel, a lot of time. When you look at a star that's 100 light-years away, you're seeing it as it was 100 years ago. When you look at a galaxy that's 1 billion light-years away, you're seeing it as it was 1 billion years ago. When you look at a galaxy that's 13 billion light-years away, you're seeing it as it was 13 billion years ago. When the universe was young, when stars were first being born. But there's a problem. The universe is expanding, it's getting bigger, all the time, and as it expands it stretches light, makes the wavelengths longer, shifts the light toward the red end of the spectrum. This is called redshift. The farther away something is, the more redshifted its light becomes. For the most distant galaxies, the light is so redshifted that it's no longer visible light. It's infrared light. Light with longer wavelengths. Light that our eyes can't see, but light that Webb can see. That's why Webb sees in infrared. That's how it can see the earliest galaxies. The first stars. The universe's first light. Infrared light is special. It has longer wavelengths than visible light. It can pass through dust clouds that block visible light. It can reveal things hidden from other telescopes. It can see the universe's earliest moments, when everything was just beginning. But seeing in infrared isn't easy. Everything gives off infrared light. Everything emits heat. Even the telescope itself, even the instruments, even the electronics. To see faint infrared light from distant galaxies, Webb has to be incredibly cold, colder than almost anything in the universe. That's why the sunshield is so important. That's why the cryocooler is essential. That's why everything has to work perfectly. To keep Webb cold, to allow it to see, to reveal the universe's secrets. In July 2022, Webb released its first images. The first deep field image was stunning. It showed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. But these weren't just any galaxies. Some of them were incredibly distant. Some of them were incredibly old. Some of them formed when the universe was just a few 100 million years old. But that was just the beginning. Webb kept observing, kept discovering, kept pushing the limits of how far back in time we can see. In May 2025, Webb discovered something extraordinary, a galaxy called MOMZ-14. The most distant galaxy ever seen. It has a redshift of 14.44. That means it formed about 280 million years after the Big Bang. Just 280 million years, when the universe was incredibly young, when stars were first being born. Astronomers studying the data found that this galaxy is remarkably luminous for its age. It's already as massive as the Small Magellanic Cloud, a nearby galaxy we can see with the naked eye. Yet it formed when the universe was less than 2% of its current age. The discovery was made during a deep field observation. Webb was staring at a tiny patch of sky for hours, collecting light from the faintest objects, from the most distant galaxies. When the data was analyzed, something stood out, a faint smudge, barely visible, but there. A galaxy, but not just any galaxy. The most distant galaxy ever seen. Astronomers calculated its distance, its redshift, its age, and the numbers were staggering. Redshift, 14.44. That meant it formed just 280 million years after the Big Bang, when the universe was incredibly young, when everything was just beginning. But here's what's surprising. The galaxy is already massive, already luminous, already complex. How did it form so quickly? How did it grow so large? We don't know. Not yet, but Webb is helping us find out. The discovery challenges our understanding of galaxy formation. We thought galaxies formed slowly, over billions of years. But MOMZ-14 shows us that they formed quickly. Very quickly. That the early universe was more active than we thought, more dynamic, more mysterious. Astronomers studying the data found that MOMZ-14 is already as massive as the Small Magellanic Cloud. Yet it formed when the universe was less than 2% of its current age. This suggests that galaxy formation happened much faster than our models predicted. Some researchers think dark matter might have played a key role, clumping together early, creating gravitational wells, where gas could collect quickly, where stars could form rapidly, where galaxies could grow large in a short amount of time. How did MOMZ-14 form so quickly? We don't know. Not yet. But scientists have ideas. Maybe dark matter played a role, clumping together, creating gravitational wells, where gas could collect, where stars could form, where galaxies could grow. Or maybe the early universe was different, more dense, more active, more conducive to galaxy formation. Maybe conditions were just right for galaxies to form quickly, to grow large, to become complex in a short amount of time. Webb is helping us find out by observing more distant galaxies, by studying their properties, by understanding how they formed, by revealing the secrets of the early universe, one discovery at a time. But MOMS 14 isn't alone. Webb has discovered other distant galaxies, other early galaxies, each one telling a story, each one revealing secrets, each one challenging our understanding. The early universe was more active than we thought, more dynamic, more mysterious, and Webb is helping us understand it. Think about that. The universe is about 13.8 billion years old. This galaxy formed when it was just 280 million years old. That's like looking at a photo of someone when they were 2 years old, and they're now 100 years old. That's how far back in time Webb is seeing. MOMS 14 is remarkable. It's incredibly luminous, bright. For such an early galaxy, it's compact, small, but it has a mass comparable to the small Magellanic Cloud, a nearby galaxy that we can see with the naked eye from the southern hemisphere. This discovery is important. It tells us that galaxies formed earlier than we thought, that they grew faster than we expected, that the early universe was more active than we imagined. It's rewriting our understanding of cosmic history. But MOMS 14 isn't the only distant galaxy Webb has discovered. There's also GZ9P3, a galaxy merger. From about 510 million years after the Big Bang, it shows a double nucleus, two bright spots, indicating that two galaxies recently merged, became one, created something bigger, something more massive. This is important. It tells us that galaxies were merging, even in the early universe. That mergers played a role in galaxy formation from the very beginning, that the universe was more dynamic than we thought. But Webb isn't just discovering distant galaxies, it's also discovering galaxies that were invisible to other telescopes, like TECC 71, a dusty star-forming galaxy that was invisible to the Hubble Space Telescope. Hubble sees invisible light, but TECC 71 is hidden behind dust clouds. Dust that blocks visible light, but dust that infrared light can pass through. Webb saw through the dust, revealed the galaxy, showed that it's forming hundreds of new stars every year, that it's a massive galaxy, that it was there all along. We just couldn't see it until Webb. This is important. It tells us that there are galaxies we've been missing, galaxies hidden behind dust, galaxies invisible to optical telescopes, but visible to Webb. It's like discovering a whole new population of galaxies that we never knew existed. Dust is everywhere in the universe, in galaxies, between galaxies, in star-forming regions. It blocks visible light, makes things invisible. But infrared light can pass through dust, can reveal what's hidden, can show us what we've been missing. TECC 71 is just one example. There are probably many more galaxies hidden behind dust, invisible to other telescopes, but visible to Webb, waiting to be discovered, waiting to be studied, waiting to reveal their secrets. These Hubble dark galaxies are important. They tell us that our census of galaxies is incomplete, that we've been missing a significant fraction, that the universe is more complex than we thought, that there's more out there than we can see with visible light. Webb is revealing these hidden galaxies, showing us what we've been missing, expanding our understanding of how many galaxies exist, of how they form, of how they evolve. The universe is bigger than we thought, more complex, more interesting. And Webb is helping us see it all. But galaxies aren't the only distant objects Webb is discovering. In December 2025, Webb observed something even more extraordinary. A supernova, the most distant supernova ever seen. called SN in GRB 250314A. The discovery was published in Astronomy and Astrophysics in December 2025, marking a major milestone in supernova research. This supernova exploded when the universe was just 730 million years old, just 730 million years after the Big Bang. When the universe was incredibly young, when stars were first being born and dying. The event was first detected by a gamma-ray burst monitor on March 14, 2025. Astronomers then used ground-based telescopes to confirm its incredible distance. Then they pointed Webb at it. About 110 days later, when the supernova had faded enough for Webb to separate its light from the faint glow of its host galaxy, the supernova was first detected by a gamma-ray burst, a flash of high-energy light. On March 14, 2025, astronomers used ground-based telescopes to confirm it was incredibly distant. Then, they pointed Webb at it. About 110 days later, when the supernova had faded enough for Webb to separate its light from the faint glow of its host galaxy. What Webb saw was surprising. The supernova looked familiar. It closely resembled SN 1998 BW, the supernova that exploded much closer to Earth in 1998. That was linked to a gamma-ray burst. Just like this one, researchers published their findings in Astronomy and Astrophysics in December 2025. They found that despite forming in an environment with very different conditions, including much lower metallicity, the star appears to have died in a familiar way. The data also ruled out a far brighter type of explosion, such as a superluminous supernova. This challenges the long-held idea that the earliest stars would produce explosions that were distinctly brighter or bluer than those seen today. This is important. It tells us that massive stars died the same way, even in the early universe, even when conditions were different. Even when there were fewer heavy elements, stars still exploded the same way. They still created the same elements. They still lit up the universe the same way. This challenges our ideas about the early universe. We thought early stars might explode differently, might be brighter, might be bluer. But they weren't. They exploded just like modern stars. They died the same way, across cosmic time. But Webb isn't just seeing distant objects, it's also seeing nearby objects, in incredible detail, like the Carina Nebula, a star-forming region, about 7,600 light-years away, in our own galaxy. Webb's image of the Carina Nebula is stunning. It shows clouds of gas and dust, in incredible detail. It shows newborn stars, bursting into existence. It shows jets of material shooting out from young stars. It shows the birth of stars, in real time. Well, as real time as you can get when you're looking 7,600 years into the past. But Webb's view is different from Hubble's. Hubble saw the nebula in visible light, showed its beautiful colors. But Webb sees it in infrared light, sees through the dust clouds, reveals stars hidden inside, shows structures invisible to other telescopes. The same is true for the pillars of creation, one of Hubble's most famous images, towers of gas and dust. In the Eagle Nebula, about 6,500 light-years away, Hubble's image was beautiful, but Webb's image is different. It sees through the dust, reveals stars forming inside the pillars, shows the process of star formation in incredible detail. The pillars of creation are iconic. They've been photographed many times by many telescopes. But Webb's view is unique. It sees in infrared light, sees through the dust, reveals what's hidden inside, shows stars forming in the pillars themselves, shows jets of material shooting out from young stars, shows the process in incredible detail. But the pillars won't last forever. They're being eroded. by radiation from nearby stars, by stellar winds, by the forces of star formation. Eventually they'll be destroyed. The stars inside will emerge. The pillars will fade away, but new pillars will form elsewhere. The cycle continues, over and over, across the galaxy. Webb's image captures this moment, this process, this cycle. It shows us how stars form, how they shape their surroundings, how they create and destroy, all at the same time. It's beautiful, it's complex, it's the cosmic life cycle in action. But Webb isn't just taking pretty pictures, it's also analyzing light, breaking it into its component colors, revealing what things are made of, how fast they're moving, how far away they are. This is called spectroscopy, and it's one of Webb's most powerful tools. By analyzing the light from distant galaxies, Webb can determine their composition, their age, their distance, their history. It can answer questions we've been asking for centuries. Spectroscopy works like this. When light passes through a gas, certain wavelengths get absorbed by specific molecules. Each molecule absorbs different wavelengths, creates a unique fingerprint, a pattern of dark lines in the spectrum of light. By analyzing these patterns, Webb can identify what gases are present, can determine the temperature, the pressure, the composition, can reveal the secrets of distant objects without ever visiting them. Webb has analyzed the light from thousands of galaxies, has determined their distances, has measured their ages, has studied their composition, has revealed the universe's history in incredible detail. But spectroscopy isn't just for galaxies. It's also for stars, for planets, for everything Webb observes. It's the key to understanding the universe, the tool that reveals its secrets. The discoveries keep coming. Every week, every month, every observation reveals something new, something unexpected, something that challenges our understanding. Take the early galaxies. We thought they would be small, simple, primitive, but Webb is showing us that they're not. They're massive, complex, already well-formed. How did they form so quickly? How did they grow so large? We don't know, not yet, but Webb is helping us find out. Or take the supernova, the most distant one ever seen. It exploded the same way as modern supernova, even though conditions were different, even though there were fewer heavy elements. Why? We don't know. Not yet. But Webb is helping us understand. The James Webb Space Telescope is seeing the first light, the light from the universe's earliest moments, the light from the first stars, the first galaxies, the first everything. It's like looking back in time, to when everything was just beginning, to when the universe was young, to when stars were first being born. Every image Webb takes is a time machine. Every observation is a journey into the past. Every discovery is a revelation about how the universe began, how it evolved, how it became what it is today. And that's just the beginning, because Webb isn't just looking at galaxies. It's also looking at planets, planets around other stars, planets that might harbor life, and that's what we'll explore next. The universe is vast, it's ancient, it's mysterious, and Webb is helping us explore it, one observation at a time, one discovery at a time, one revelation at a time. The journey into the past continues. The exploration of the early universe goes on, the mysteries await, and Webb is our guide. Chapter 4: Worlds Beyond Our Solar System. For most of human history, we only knew about the planets in our own solar system. 9 planets. Or 8 if you don't count Pluto. But they were all we had, all we knew existed, all we could study. But that changed in 1995, when astronomers discovered the first planet around another star. An exoplanet. A planet orbiting a sun-like star. called 51 Pegasi b. It was a hot Jupiter, a gas giant, orbiting very close to its star. Too close for life. But it proved that planets existed around other stars. That our solar system wasn't unique, that planets were common. Since then, astronomers have discovered thousands of exoplanets, using different methods, different telescopes, different techniques. But most of these discoveries were just that, discoveries. We knew the planets existed, but we didn't know much about them. What were they made of? Did they have atmospheres? Could they support life? The James Webb Space Telescope is changing that. It's not just discovering exoplanets. It's studying them, analyzing their atmospheres, determining their composition, looking for signs of life. It's revolutionizing exoplanet science. Here's how it works. When an exoplanet passes in front of its star, it blocks some of the star's light. This is called a transit. During a transit, some of the star's light passes through the planet's atmosphere. If the planet has an atmosphere, that light gets filtered. Certain wavelengths get absorbed by molecules in the atmosphere. By analyzing which wavelengths are absorbed, Webb can determine what the atmosphere is made of, can detect water vapor, carbon dioxide, methane, other gases, can look for signs of life, biosignatures, gases that might be produced by living things. Webb's first exoplanet observation was WASP-96b, a hot Jupiter, about 150 light-years away, orbiting very close to its star, completing an orbit in just 3.5 days. It's incredibly hot. About 800 degrees Fahrenheit, too hot for life, but perfect for studying atmospheres. When Webb analyzed the light passing through this planet's atmosphere, it detected water vapor, clear signs of water, in a planet's atmosphere. For the first time, we could see what an exoplanet's atmosphere was made of. Not just guess, but actually see. The observation was a test. Could Webb detect an exoplanet atmosphere? Could it analyze the light? Could it reveal the planet's secrets? The answer was yes. Yes, it could. Webb observed WASP-96b during a transit. As the planet passed in front of its star, Webb collected light that had passed through the planet's atmosphere. Light that carried information about what the atmosphere was made of. When the data was analyzed, the results were clear. The atmosphere contained water vapor. Lots of it. This was the first time Webb had detected water in an exoplanet atmosphere. But it wouldn't be the last. The discovery was exciting. It proved that Webb could study exoplanets, that it could analyze their atmospheres, that it could reveal their secrets. It opened the door to studying more planets, to finding water, to searching for life. But WASP-96b was just the beginning. Webb has since studied dozens of exoplanets, has detected water vapor in many of them, has found other gases, has revealed the diversity of exoplanet atmospheres, has shown that planets come in many forms, with many different compositions. Webb observed WASP-96b during a transit, analyzed the light passing through its atmosphere, and made a stunning discovery. The atmosphere contains water vapor, lots of it. This was the first time Webb had detected water in an exoplanet atmosphere. But it wouldn't be the last. Since then, Webb has studied dozens of exoplanets, has detected water vapor in many of them, has found carbon dioxide, methane, other gases, has revealed the diversity of exoplanet atmospheres, has shown that planets come in many forms, with many different atmospheres. But some of Webb's discoveries are truly strange. Like PSRJ 232222650b, a gas giant orbiting a pulsar about 750 light-years away. A pulsar is a rapidly spinning neutron star, the remnant of a supernova. It emits beams of radiation, like a cosmic lighthouse. PSRJ 23222650b orbits, very close to its pulsar, completing an orbit in just a few hours. It's incredibly hot. And its atmosphere is unlike anything we've seen before. Webb analyzed the planet's atmosphere and found something surprising. It's rich in carbon and helium. But it contains no water, no methane, no carbon dioxide, nothing we'd expect to find in a planet's atmosphere. According to research published in 2024, the planet's upper layers contain soot clouds, dark clouds made of carbon particles. And deeper layers might contain diamonds, formed under high pressure, from the carbon in the atmosphere. Scientists estimate the pressure in those deeper layers could be millions of times greater than Earth's atmospheric pressure. Under those conditions, carbon could crystallize into diamonds, creating a planet with diamond clouds, and, potentially, diamond rain. It's unlike anything we've seen before. Instead, the upper layers contain soot clouds, dark clouds, made of carbon particles, and deeper layers might contain diamonds, formed under high pressure, from the carbon in the atmosphere. This is strange, very strange. It challenges our understanding of planetary formation. How did this planet form? Why does it have such a strange atmosphere? What processes created the soot clouds, the potential diamonds? We don't know, not yet, but Webb is helping us find out. By studying planets like this, by analyzing their atmospheres, by revealing their secrets. The Diamond Planet is a reminder that the universe is full of surprises, that planets come in many forms, that our understanding is incomplete, that there's always more to discover, always more to learn, always more mysteries to solve. But the Diamond Planet isn't alone. Webb has discovered other strange planets, planets with unusual atmospheres, planets that challenge our understanding. Each one is unique, each one tells a story, each one reveals secrets about how planets form, about how they evolve, about what's possible. The diversity is incredible. Hot Jupiters, rocky worlds, gas giants, ice giants, planets orbiting pulsars, planets in binary systems, planets we've never imagined. But Webb is finding them, studying them, revealing their secrets, one observation at a time. But not all exoplanets are strange. Some are more familiar, like WASP 107b, another hot Jupiter. About 200 light-years away, Webb studied its atmosphere and found something interesting. It contains hydrogen sulfide, ammonia, carbon dioxide, methane, sulfur dioxide, a complex mix of chemicals that tells us about the planet's formation, its history, its composition. But the most exciting exoplanets are the ones that might harbor life. Rocky planets in the habitable zone, where liquid water could exist, where life might be possible. The TRAPPIST-1 system is one of the most promising. It's a red dwarf star, about 40 light-years away. Smaller than the Sun, cooler than the Sun. But it has 7 planets, all rocky, all about the size of Earth. And 3 of them are in the habitable zone, where liquid water could exist on their surfaces. Astronomers discovered this system in 2016, using ground-based telescopes. But Webb is the first telescope powerful enough to study these planets in detail, to analyze their atmospheres, to look for signs of life. Initial observations suggest that some of these planets might have thin atmospheres. But the data is still being analyzed. The search continues. Because finding life in this system would be one of the greatest discoveries in human history. The system was discovered in 2016. by the TRAPPIST telescope in Chile. It immediately captured attention. 7 Earth-sized planets around a single star. 3 in the habitable zone. It was unprecedented, it was exciting, it was promising. But studying these planets is difficult. They're small, they're faint. They're far away. But Webb is up to the challenge. It's been observing the TRAPPIST-1 planets, analyzing their atmospheres, looking for signs of life. So far, Webb hasn't found definitive signs of life. But it has found something interesting. Some of the planets might have atmospheres, thin atmospheres, but atmospheres nonetheless. And some might have water vapor in their atmospheres or on their surfaces. The search continues. Webb will keep observing, keep analyzing, keep looking. Because finding life beyond Earth would be one of the greatest discoveries in human history. It would change everything. It would prove that we're not alone, that life is common, that the universe is full of possibilities. But finding life isn't easy. It requires the right conditions, the right atmosphere, the right temperature, the right composition, and we're just beginning to understand what those conditions might be. Webb is helping us understand by studying exoplanets, by analyzing their atmospheres, by revealing their secrets, by showing us what's possible, what might exist, what we might find. The search for life is one of humanity's greatest quests. Are we alone? Is there life beyond Earth? These questions have haunted us for centuries. But now, for the first time, we have the tools to answer them. Webb is one of those tools. It can detect biosignatures, signs of life, in exoplanet atmospheres. But what are biosignatures? They're gases that might be produced by living things, like oxygen, methane, in certain combinations. These gases could indicate the presence of life. But they could also be produced by non-living processes. So we have to be careful. We have to look for multiple signs. We have to be sure. Webb is helping us understand what to look for by studying exoplanets, by analyzing their atmospheres, by revealing their composition, by showing us what's possible, what might exist, what we might find. The search continues. Webb will keep observing, keep analyzing, keep looking. Because finding life beyond Earth would be one of the greatest discoveries in human history. It would change everything. It would prove that we're not alone, that life is common, that the universe is full of possibilities. Webb has been studying the TRAPPIST-1 planets, analyzing their atmospheres, looking for signs of life, biosignatures, gases that might be produced by living things. So far, Webb hasn't found definitive signs of life. But it has found something interesting. Some of the planets might have atmospheres. Thin atmospheres. But atmospheres nonetheless. And some might have water vapor in their atmospheres or on their surfaces. The search continues. Webb will keep observing, keep analyzing, keep looking for signs of life. Because finding life beyond Earth would be one of the greatest discoveries in human history. It would change everything. It would prove that we're not alone, that life is common, that the universe is full of possibilities. But finding life isn't easy. It requires the right conditions, the right atmosphere, the right temperature, the right composition, and we're just beginning to understand what those conditions might be. Webb is helping us understand by studying exoplanets, by analyzing their atmospheres, by revealing their secrets, by showing us what's possible, what might exist, what we might find. But exoplanets aren't the only things Webb is studying. It's also studying the disks around young stars, the places where planets form, the birthplaces of worlds. Webb has observed several protoplanetary disks of gas and dust, around young stars, where planets are forming, where new worlds are being born. These observations are revealing how planets form, how they grow, how they evolve. They're showing us the process of planet formation in real time. Well, as real time as you can get when you're looking hundreds of light years away. In one study, Webb detected water vapor in a protoplanetary disk around a young star. The disk contained enough water to fill Earth's oceans thousands of times over. But it also detected organic molecules, carbon-based compounds, the building blocks of life. This suggests that the ingredients for life might be common, might be everywhere, might be waiting for the right conditions to form planets, to create life. Protoplanetary disks are beautiful. They're like cosmic nurseries, where planets are born, where new worlds are created. They're full of gas and dust that clumps together, forms planets, over millions of years. Webb's infrared vision is perfect for studying these disks. It can see through the dust, reveal the structure, show how planets form. In incredible detail, it can detect water, organic molecules, the building blocks of life in these disks, showing us that the ingredients for life are common, are everywhere, are waiting for the right conditions. The observations are revealing surprises. Some disks have gaps, where planets have already formed, clearing out material, creating paths. Other disks are smooth, still forming, still evolving. Each one is unique. Each one tells a story. Each one reveals secrets about how planets form, about how solar systems evolve, about what's possible. These observations are important. They're helping us understand how our own solar system formed, how planets are created, how common they might be. They're showing us that planet formation is a process that takes time, that creates diversity, that results in worlds like our own, and worlds unlike anything we've imagined. But the most exciting discoveries are still to come. Webb will keep observing, keep discovering, keep revealing the secrets of exoplanets, keep looking for signs of life, keep pushing the limits of what we can see, what we can know, what we can discover. The search for life is one of humanity's greatest quests. Are we alone? Is there life beyond Earth? Webb is helping us answer these questions by studying exoplanet atmospheres, by looking for biosignatures, by revealing what's possible. Biosignatures are signs of life, gases that might be produced by living things, like oxygen, methane. In certain combinations, these gases could indicate the presence of life. But they could also be produced by non-living processes. So we have to be careful. We have to look for multiple signs. We have to be sure. Webb is helping us understand what to look for by studying exoplanets, by analyzing their atmospheres, by revealing their composition, by showing us what's possible, what might exist, what we might find. The James Webb Space Telescope is revolutionizing exoplanet science. It's not just discovering planets, it's studying them, analyzing them, revealing their secrets. It's showing us that planets are diverse, that they come in many forms, with many different atmospheres, many different compositions. Some exoplanets are hot Jupiters, gas giants, orbiting very close to their stars, too hot for life, but perfect for studying atmospheres. Others are rocky worlds, in the habitable zone, where liquid water could exist, where life might be possible. Some have thick atmospheres, dense, cloudy, hard to see through. Others have thin atmospheres, clear, transparent, easy to study. Some have water vapor, others don't. Some have carbon dioxide, others have methane. The diversity is incredible, and it's just getting started. There are thousands of exoplanets waiting to be studied, thousands of atmospheres waiting to be analyzed, thousands of secrets waiting to be revealed. But exoplanets aren't the only things Webb is studying. It's also studying stars, the birth of stars, the death of stars, the life cycle of stars. And that's what we'll explore next. Every exoplanet observation is a step forward. Every atmosphere analyzed is a clue. Every discovery is progress toward answering the biggest question of all. Are we alone? Webb is helping us find out. One observation at a time. One discovery at a time. One revelation at a time. Chapter 5. The Cosmic Life Cycle. Stars are born, they live, they die. It's the cosmic life cycle, the cycle that creates everything. The elements that make up planets, the elements that make up life, the elements that make up you. But we've never seen this cycle in detail, not until now. Not until the James Webb Space Telescope. Webb is revealing the birth of stars, the death of stars, the entire life cycle, in incredible detail. Let's start with star birth. Stars form in clouds of gas and dust, called nebulae. These clouds are cold, dark, dense. Gravity pulls the gas and dust together, forms clumps. The clumps grow, get denser, get hotter. Eventually, nuclear fusion begins. A star is born. But this process is hidden behind dust clouds that block visible light, that hide the birth of stars. But Webb sees in infrared light, light that can pass through dust, light that reveals what's hidden. Webb's image of the Carina Nebula shows this beautifully. It's a star-forming region, about 7,600 light-years away, in our own galaxy. Webb's image shows clouds of gas and dust. In incredible detail, it shows newborn stars, bursting into existence. It shows jets of material, shooting out from young stars. It shows the birth of stars in real time. The Carina Nebula is one of the largest star-forming regions in our galaxy. It's home to thousands of stars, in various stages of formation. Some are just beginning to form. Others are already shining brightly. Some are still hidden behind clouds of gas and dust. Webb's infrared vision sees through the dust, reveals stars hidden inside, shows structures invisible to other telescopes. The image is stunning, more detailed than anything we've seen before. It shows the process of star formation in incredible detail. But the Carina Nebula isn't just beautiful. It's also scientifically important. It's helping us understand how stars form, how they grow, how they evolve. It's showing us the process, step by step, in real time. Well, as real time as you can get when you're looking 7,600 years into the past. The nebula is also home to some of the most massive stars known. Stars that are hundreds of times more massive than the Sun. Stars that will live fast, die young, explode as supernovae, scatter their elements into space, create the building blocks for new stars, new planets, new life. Webb's observations of the Carina Nebula are revealing these processes, showing us how massive stars form, how they live, how they die, how they shape their surroundings, how they influence star formation, how they create the elements of life. But the Tarantula Nebula is even more impressive. It's in the Large Magellanic Cloud, a nearby galaxy, about 160,000 light-years away. It's one of the largest star-forming regions we know of, and Webb's image is stunning. The Tarantula Nebula is a star factory. It's forming thousands of new stars right now. As we speak. Well, as we observe. Webb's image shows the process. Shows the clouds of gas and dust. Shows the newborn stars. Shows the jets of material. Shows everything. In incredible detail. Astronomers studying Webb's observations found that the nebula contains over 800,000 stars, in various stages of formation. Some are just beginning to collapse. Others are already shining brightly. Some are still hidden, behind clouds of gas and dust. The nebula is so active that it's creating new stars at a rate of about 1 per year. That might not sound like much, but over millions of years that adds up to thousands of stars, to entire star clusters, to the building blocks of galaxies. But Webb isn't just seeing star birth, it's also seeing star death, the end of the life cycle, when massive stars explode, when they create supernovae, when they scatter their elements into space. Star death is dramatic. When a massive star runs out of fuel, it collapses. The core collapses. In seconds, the outer layers explode outward. In a supernova, one of the most energetic events in the universe. The process is violent. The core collapses under its own weight. In seconds, the pressure increases, the temperature rises, nuclear reactions accelerate. Then everything explodes. The outer layers are blown away at incredible speeds. The core becomes a neutron star or a black hole. The explosion scatters elements into space, elements that were created in the star's core over millions of years. These elements are essential. They form new stars, new planets, new life. Without supernovae, the universe would be different, simpler, less complex, less interesting. Supernovae are the universe's way of creating, of recycling, of making new things from old. But not all stars die in supernovae. Smaller stars like our Sun die more gently. They expand, become red giants, shed their outer layers, create planetary nebulae, beautiful shells of gas that glow in the light of the dying star. Then the core cools, becomes a white dwarf, a dense remnant that slowly fades away. Webb is observing both types of stellar death, the violent supernovae, the gentle planetary nebulae. Both are beautiful, both are important, both are part of the cosmic life cycle, both create elements, both scatter material, both contribute to the universe's evolution. A supernova can outshine entire galaxies for a brief moment. Then it fades, leaves behind a neutron star or a black hole, and scatters elements into space. Elements that were created in the star's core through nuclear fusion over millions of years. These elements are essential. They form new stars, new planets, new life. Without supernovae, the universe would be different, simpler, less complex, less interesting. Supernovae are the universe's way of creating, of recycling, of making new things from old. Webb is observing supernovae in incredible detail, seeing them explode, watching them fade, studying their remnants, understanding how they work, how they create elements, how they shape the universe. But Webb isn't just observing nearby supernovae. It's also observing the most distant ones, like SN in GRB 250314a. The most distant supernova ever seen. Exploded when the universe was just 730 million years old. Just 730 million years after the Big Bang. What Webb saw was surprising. The supernova looked familiar. It closely resembled supernovae we see today. In the nearby universe, it exploded the same way, created the same elements, lit up the universe the same way. This is important. It tells us that massive stars died the same way, even in the early universe. Even when conditions were different, stars still exploded, still created elements, still scattered material into space. The cosmic life cycle was the same. From the very beginning, the Southern Ring Nebula shows this beautifully. It's a planetary nebula, the remains of a dying star. About 2,000 light-years away, the star has shed its outer layers, created a beautiful shell of gas and dust that glows in infrared light. Webb's image shows the nebula in incredible detail, shows the layers of gas, shows the dust, shows the dying star at the center, shows the entire process, the death of a star, the creation of new elements, the scattering of material into space. But supernovae are even more dramatic. When a massive star explodes, it creates a supernova, one of the most energetic events in the universe. It can outshine entire galaxies for a brief moment. Then it fades, leaves behind a neutron star or a black hole, and scatters elements into space. In December 2025, Webb observed something extraordinary, the most distant supernova ever seen, called SN in GRB 250314a. It exploded when the universe was just 730 million years old, just 730 million years after the Big Bang. What Webb saw was surprising. The supernova looked familiar. It closely resembled supernovae we see today. In the nearby universe, it exploded the same way, created the same elements, lit up the universe the same way. This is important. It tells us that massive stars died the same way, even in the early universe. Even when conditions were different, stars still exploded, still created elements, still scattered material into space. The cosmic life cycle was the same from the very beginning. But supernovae aren't the only way stars die. Sometimes, two neutron stars collide, create a kilonova, an explosion that creates heavy elements, like gold, platinum, uranium, elements that can't be created in normal supernova. In August 2025, Webb observed something even more extraordinary, a superkilonova, a hybrid explosion, combining a supernova and a kilonova, called AT2025 ALTS. It was the first of its kind ever detected, and it's helping us understand how stars die, how elements are created, how the universe evolves. But stars aren't the only things that live and die. Galaxies do too. They form, they evolve, they merge, they change. Over billions of years, Webb is revealing this process by observing distant galaxies, by seeing them as they were billions of years ago, by watching them evolve over cosmic time. Stefan's quintet shows this beautifully. It's a group of 5 galaxies, about 290 million light-years away. 4 of them are interacting, merging, creating something new, something bigger, something more massive. Webb's image shows the process, shows the galaxies, shows the gas and dust between them, shows the stars being formed, shows the entire interaction, in incredible detail. But Webb is also seeing galaxy mergers in the early universe, like GZ9P3, a galaxy merger, from about 510 million years after the Big Bang. It shows a double nucleus, 2 bright spots, indicating that 2 galaxies recently merged, became one, created something bigger. This is important. It tells us that galaxies were merging, even in the early universe, that mergers played a role in galaxy formation from the very beginning, that the universe was more dynamic than we thought. But galaxies aren't just merging, they're also growing, forming new stars, creating new elements, evolving. Over billions of years. Webb is revealing this process by observing galaxies at different distances, at different ages, by seeing how they change over cosmic time. But galaxies also contain black holes, supermassive black holes. At their centers, these black holes grow over billions of years by consuming gas, by merging with other black holes, by growing larger and larger. Webb has discovered some of the most ancient black holes ever seen, like Kappa's LRDZ9, a black hole from about 500 million years after the Big Bang. It's already massive, already growing, already influencing its galaxy. Research published in 2024 found that this black hole is rapidly growing. It's already millions of times more massive than our Sun, yet it formed when the universe was incredibly young. This challenges our understanding of black hole formation. We thought black holes grew slowly, over billions of years. But Kappa's LRDZ9 shows us that they grew fast. Very fast. Some astronomers think these early black holes might have formed directly from collapsing gas clouds, bypassing the star stage entirely, creating massive black holes right from the start. This is surprising. We didn't expect black holes to grow so quickly, to become so massive so early in the universe's history. But Webb is showing us that they did, that black holes were common, that they grew fast, that they played a role in galaxy formation from the very beginning. Black holes are mysterious. They're regions of space where gravity is so strong that nothing can escape, not even light. They're invisible, but we can detect them by their effects on nearby matter, on light, on the motion of stars. Supermassive black holes are the largest, millions or billions of times more massive than the Sun. They sit at the centers of galaxies, including our own Milky Way. They grow by consuming gas, by merging with other black holes, by accreting matter, over billions of years. But how did they form? How did they grow so large, so quickly? These are questions Webb is helping answer. By observing ancient black holes, by studying their properties, by understanding how they formed, how they grew, how they influenced galaxy formation. The discoveries are surprising. Black holes were forming even in the early universe, even when galaxies were just beginning. They were growing fast, becoming massive, influencing their surroundings, shaping galaxy evolution from the very beginning. This challenges our understanding of black hole formation, of galaxy evolution, of the early universe. But that's what science does. It challenges, it questions, it reveals, and Webb is helping us understand, one discovery at a time. But black holes aren't the only things Webb is discovering. It's also discovering new populations of objects, things we've never seen before, things we didn't know existed, like compact emission line objects, point-like objects, at high redshifts, with strong emission lines. That could be low luminosity active galactic nuclei, or young star-forming galaxies. We don't know yet. Not for sure. But Webb is helping us find out. Research published in 2024 described a new population of these objects. They have redshifts between 3.6 and 5.4. That means they formed when the universe was between 1.5 and 2 billion years old. They're compact, point-like, with strong emission lines. But their exact nature is still being debated. Some astronomers think they're low luminosity active galactic nuclei, black holes at the centers of galaxies, that are just beginning to grow. Others think they're young star-forming galaxies, that are forming stars at incredible rates. Only more observations will tell us for sure. But the most important thing Webb is revealing is the cosmic life cycle, the cycle that creates everything. The birth of stars, the death of stars, the formation of galaxies, the evolution of the universe. Everything is connected. Stars are born from gas and dust. They live. They die. They scatter elements into space. Those elements form new stars, new planets, new life. The cycle continues, over and over, across billions of years. Webb is showing us this cycle, in incredible detail. From the birth of the first stars, to the death of stars today. From the formation of the first galaxies, to the evolution of galaxies now. From the beginning of everything, to the present day. The cosmic life cycle is beautiful, it's complex, it's mysterious. And Webb is helping us understand it, one observation at a time, one discovery at a time, one revelation at a time. But the discoveries aren't stopping. Webb keeps observing, keeps discovering, keeps revealing the birth of stars, the death of stars, the formation of galaxies, the evolution of the universe, everything. In incredible detail. The cosmic life cycle is beautiful, it's complex, it's mysterious. And Webb is helping us understand it, one observation at a time. One discovery at a time, one revelation at a time. Stars are born from gas and dust. They live for millions or billions of years. They create elements through nuclear fusion. They die in spectacular explosions. They scatter their elements into space. Those elements form new stars, new planets, new life. The cycle continues, over and over, across billions of years. Webb is showing us this cycle, from beginning to end, from birth to death, from creation to destruction, and back to creation again. It's showing us how everything is connected, how everything depends on everything else, how the universe is one great cycle of birth, life, death, and rebirth. But the cycle isn't just about stars, it's also about galaxies. Galaxies form, they evolve, they merge, they change, over billions of years. They create stars, they destroy stars, they shape the universe, they are shaped by it. Webb is revealing this process by observing galaxies at different distances, at different ages, by seeing how they change over cosmic time, by understanding how they form, how they evolve, how they become what they are. And that's just the beginning, because Webb isn't just revealing what we know, it's also revealing what we don't know, the mysteries, the questions, the things that challenge our understanding, and that's what we'll explore next. The cosmic life cycle is everywhere, in every star, in every galaxy, in every corner of the universe. It's the story of everything, the history of the cosmos, written in light, traveling through space, waiting to be seen. And Webb is seeing it, revealing it, helping us understand it. Chapter 6: The Future and the Mysteries. The James Webb Space Telescope is rewriting our understanding of the universe. There's no doubt about it, it's discovering things we never expected, revealing mysteries we didn't know existed, challenging ideas we thought were settled. But here's the thing, every discovery raises new questions, every answer leads to new mysteries, every revelation shows us how much we still don't know. Take the most distant galaxies. Webb has discovered galaxies that formed just 280 million years after the Big Bang. That's incredibly early. Incredibly fast. We didn't expect galaxies to form so quickly, to grow so large, so early in the universe's history. Zeb 14 is a perfect example. It's the most distant galaxy ever seen, formed just 280 million years after the Big Bang. But it's already massive, already luminous, already complex. How did it form so quickly? How did it grow so large? We don't know. Not yet. GZ9P3 is another example, a galaxy merger. From about 510 million years after the Big Bang. It shows that galaxies were merging, even in the early universe. But how? Why? What processes drove these mergers? We don't know. Not yet. These discoveries challenge our understanding of galaxy formation. We thought galaxies formed slowly, over billions of years. But Webb is showing us that they formed quickly. Very quickly. That the early universe was more active than we thought. More dynamic. More mysterious. But galaxies aren't the only mysteries. There's also the supernova. SN in GRB 250314a. The most distant supernova ever seen. It exploded when the universe was just 730 million years old. But it looked familiar. It exploded the same way as modern supernova. Even though conditions were different, even though there were fewer heavy elements. Why? Why did early stars explode the same way? Why didn't they explode differently? We don't know, not yet, but Webb is helping us find out. Then there are the exoplanets. Webb has discovered planets with strange atmospheres. Like PSRJ 23222650b. The diamond planet. With soot clouds. And potential diamonds. How did it form? Why does it have such a strange atmosphere? We don't know, not yet. But Webb is helping us find out, by studying these planets, by analyzing their atmospheres, by revealing their secrets, one observation at a time. But the biggest mystery might be life. Are we alone? Is there life beyond Earth? Webb is looking, searching, analyzing. But so far we haven't found definitive signs of life. Not yet. But the search continues. Webb will keep observing, keep analyzing, keep looking. Because finding life beyond Earth would be one of the greatest discoveries in human history. It would change everything. It would prove that we're not alone, that life is common, that the universe is full of possibilities. But Webb isn't just revealing mysteries, it's also revealing things we didn't know existed, like AS-TECC71. A galaxy that was invisible to other telescopes, hidden behind dust, but visible to Webb. How many more galaxies are hidden? How many are we missing? We don't know. Not yet. Then there are the compact emission line objects, new populations of objects, at high redshifts, that we've never seen before. What are they? What do they tell us about the universe? We don't know, not yet. But Webb is helping us find out, by observing these objects, by analyzing their light, by revealing their secrets, one discovery at a time. But Webb isn't just revealing what we don't know, it's also revealing what we might never know. The limits of what we can see, the limits of what we can understand. Webb can see incredibly far, billions of light years. But it can't see forever. There's a limit. A point beyond which we can't see. The cosmic dark ages. The period before the first stars formed. Before the first galaxies. Before there was light to see. We might never see that period, never know what happened, never understand how everything began, but Webb is getting us closer, closer than we've ever been before. The cosmic dark ages lasted for hundreds of millions of years. After the Big Bang, before the first stars, before there was light to see. It's a period we might never observe directly, but we can study it indirectly. By observing the first stars, the first galaxies, the first light. Webb is helping us understand this period, by seeing the first galaxies, by studying their properties, by understanding how they formed, by revealing what happened during the cosmic dark ages, by getting us closer to the beginning, to the Big Bang, to everything. But there are limits, even for Webb. There's a point beyond which we can't see. A time before which light didn't exist. A period we might never understand. But that's okay. Because what we can see is incredible. What we can understand is amazing. What we can discover is inspiring. The universe is vast, it's mysterious, it's beautiful, and Webb is helping us explore it. To understand it, to appreciate it, to see it in ways we've never seen before. The journey continues, the exploration goes on, the mysteries await, and Webb is our guide. But Webb won't last forever. It's designed to operate for at least 10 years, maybe 20, if the fuel lasts. But eventually it will run out of fuel, will stop working. We'll become a piece of space junk, floating in space, forever. The fuel is used for station keeping, for maintaining Webb's position at L2, for small adjustments, for keeping the telescope pointed. But there's only so much fuel. Once it's gone, Webb can't maintain its position. It will drift, it will stop working, its mission will end. But that's okay. Because by then, Webb will have made incredible discoveries, will have answered fundamental questions, will have inspired generations, will have changed how we see the universe. Forever. And when Webb's mission ends, new telescopes will take its place, new missions will be designed, new discoveries will be made, the exploration will continue. The journey will go on, the mysteries will be revealed, one discovery at a time. The legacy of Webb will last, long after the telescope stops working. Its discoveries will fuel research. For decades, its images will inspire. For generations, its revelations will change how we understand the universe. Forever. But by then new telescopes will be planned, new missions will be designed, new discoveries will be waiting, the search will continue, the exploration will go on. The mysteries will be revealed, one discovery at a time. But Webb's legacy will last, its discoveries will fuel research for decades, its images will inspire generations. Its revelations will change how we see the universe, forever. The James Webb Space Telescope is more than just a telescope, it's a window into the universe. A time machine. A tool for discovery. A symbol of human curiosity. Human ambition. Human wonder. It's proof that when we dream big, when we work together, when we refuse to give up, we can achieve the impossible. It's a testament to human ingenuity, to our drive to explore, to our need to understand. Webb is inspiring the next generation, young scientists, young engineers, young explorers, who see Webb's images, who read about its discoveries, who dream of making their own, who will build the next generation of telescopes, who will make the next discoveries, who will continue the journey into the cosmos, into the unknown, into everything. The impact of Webb extends beyond science. Its images are beautiful, they inspire, they move, they connect us to the universe, to each other, to something bigger than ourselves. People around the world have been moved by Webb's images, have been inspired by its discoveries, have been reminded of the beauty of the universe, of the wonder of exploration, of the power of human curiosity. Webb is more than just a telescope, it's a symbol of what we can achieve when we dream big, when we work together, when we refuse to give up. It's proof that the impossible is possible, that the universe is waiting, that the mysteries await, and that we can discover them, one observation at a time. It's showing us the universe's first light, the birth of stars, the death of stars, the formation of galaxies, the evolution of everything, it's revealing mysteries, answering questions, raising new questions, challenging our understanding, rewriting our knowledge. But most importantly, it's inspiring us, inspiring the next generation, inspiring future scientists, inspiring everyone who looks up at the night sky and wonders, what's out there? What are we missing? What will we discover next? The future is full of possibilities, full of discoveries, full of mysteries, and Webb is just getting started. There are decades of observations ahead, decades of discoveries waiting, decades of revelations to come. The universe is vast, it's mysterious, it's beautiful, and Webb is helping us explore it, one observation at a time, one discovery at a time, one revelation at a time. The journey continues, the exploration goes on, the mysteries await, and Webb is our guide, our window, our time machine, into the universe's deepest secrets. But Webb isn't just revealing mysteries, it's also answering questions. Questions we've been asking for centuries. How did the universe begin? How did galaxies form? How did stars first ignite? Webb is helping us find answers, one observation at a time. But every answer raises new questions. Every discovery reveals new mysteries. Every revelation shows us how much we still don't know. And that's exciting. That's what drives science forward. That's what keeps us exploring. The universe is vast. It's mysterious. It's beautiful. And Webb is helping us explore it, to understand it, to appreciate it, to see it in ways we've never seen before. The future is full of possibilities, full of discoveries, full of revelations. Webb is just getting started. There are decades of observations ahead. Decades of discoveries waiting, decades of mysteries to solve. And when Webb's mission ends, new telescopes will take its place, new missions will be designed, new discoveries will be made, the exploration will continue, the journey will go on, the mysteries will be revealed, one discovery at a time. The James Webb Space Telescope is more than just a telescope, it's a symbol of human curiosity, of our drive to explore, of our need to understand. It's proof that when we dream big, when we work together, when we refuse to give up, we can achieve the impossible. The universe is waiting, full of secrets, full of mysteries, full of wonders. And Webb is our guide, our window, our time machine, into the cosmos, into the past, into the future, into everything. But Webb isn't just revealing mysteries, it's also answering questions. Questions we've been asking for centuries. How did the universe begin? How did galaxies form? How did stars first ignite? Webb is helping us find answers, one observation at a time. But every answer raises new questions. Every discovery reveals new mysteries. Every revelation shows us how much we still don't know. And that's exciting. That's what drives science forward. That's what keeps us exploring. The universe is vast. It's mysterious. It's beautiful. And Webb is helping us explore it. To understand it. To appreciate it. To see it in ways we've never seen before. The future is full of possibilities. Full of discoveries. Full of revelations. Webb is just getting started. There are decades of observations ahead. Decades of discoveries waiting. Decades of mysteries to solve. And when Webb's mission ends, new telescopes will take its place, new missions will be designed. New discoveries will be made. The exploration will continue. The journey will go on. The mysteries will be revealed. One discovery at a time. The James Webb Space Telescope is more than just a telescope. It's a symbol of human curiosity, of our drive to explore, of our need to understand. It's proof that when we dream big, when we work together, when we refuse to give up, we can achieve the impossible. The universe is waiting, full of secrets, full of mysteries, full of wonders. And Webb is our guide, our window, our time machine. Into the cosmos, into the past, into the future, into everything. And now, the stars begin to dim behind your thoughts. We've drifted through an incredible journey, from the dream of seeing the first stars, to the reality of the James Webb Space Telescope, from the engineering marvels that make Webb possible, to the stunning discoveries it's already made. You've explored the golden mirror, the sunshield the size of a tennis court, the incredible precision that lets Webb see billions of light-years away. You've witnessed the most distant galaxy ever seen, the most distant supernova ever observed, exoplanets with diamond clouds and soot-filled atmospheres. You've seen the birth of stars, the death of stars, the formation of galaxies, the evolution of the universe, everything, in incredible detail. The James Webb Space Telescope is rewriting our understanding of the universe. There's no doubt about it. It's discovering things we never expected, revealing mysteries we didn't know existed, challenging ideas we thought were settled. But here's the thing, every discovery raises new questions. Every answer leads to new mysteries. Every revelation shows us how much we still don't know. The universe is vast, it's mysterious, it's beautiful. And Webb is helping us explore it, one observation at a time, one discovery at a time, one revelation at a time. Tonight, as you rest, Webb is still observing, still discovering, still revealing the universe's deepest secrets, the first stars, the first galaxies, the first everything. You are part of this universe. Not just a passenger on Earth, but a participant in its long and luminous unfolding. The atoms in your body were forged in stars. The elements that make you were created in supernovae. The universe's history is written in your very being. Tonight, as you rest, the universe continues. Stars are being born, stars are dying, galaxies are forming, the cosmic life cycle continues, over and over, across billions of years. And Webb is watching, observing, discovering, revealing the universe's deepest secrets, one observation at a time. If you happen to still be awake, you can go ahead and watch the next episode. But if you're drifting off, that's perfect too. Let the mysteries of the universe carry you into sleep. Let the wonder of discovery fill your dreams. The James Webb Space Telescope is rewriting our understanding of the universe. There's no doubt about it. It's discovering things we never expected, revealing mysteries we didn't know existed, challenging ideas we thought were settled. But here's the thing, every discovery raises new questions. Every answer leads to new mysteries. Every revelation shows us how much we still don't know. And that's what makes science exciting. That's what drives exploration forward. That's what keeps us wondering. The universe is vast, it's mysterious, it's beautiful, and Webb is helping us explore it one observation at a time. One discovery at a time. One revelation at a time. Tonight, as you rest, Webb is still observing, still discovering, still revealing the universe's deepest secrets. The first stars, the first galaxies, the first everything. You are part of this universe, not just a passenger on Earth, but a participant in its long and luminous unfolding. The atoms in your body were forged in stars. The elements that make you were created in supernovae. The universe's history is written in your very being. Tonight, as you rest, the universe continues. Stars are being born, stars are dying, galaxies are forming. The cosmic life cycle continues, over and over, across billions of years. And Webb is watching, observing, discovering, revealing the universe's deepest secrets, one observation at a time. The journey continues, the exploration goes on, the mysteries await, and Webb is our guide, our window, our time machine, into the cosmos, into everything. If you happen to still be awake, you can go ahead and watch the next episode, but if you're drifting off, that's perfect too. Let the mysteries of the universe carry you into sleep. Let the wonder of discovery fill your dreams. The James Webb Space Telescope has already changed everything. In just a few years of operation, it's rewritten our understanding of the universe. It's discovered the most distant galaxies, the most distant supernovae, exoplanets with strange atmospheres, black holes from the universe's infancy. But this is just the beginning. Webb has decades of observations ahead, decades of discoveries waiting, decades of mysteries to solve. The journey continues. The exploration goes on. The wonder remains. Every observation Webb makes is a step forward. Every discovery is progress. Every revelation is a gift. To humanity, to science, to understanding. The universe is vast. It's mysterious, it's beautiful. And Webb is helping us explore it, one observation at a time. The impact of Webb will last, long after its mission ends. Its discoveries will fuel research. For decades, its images will inspire. For generations, its revelations will change how we understand the universe. Forever. But most importantly, Webb is inspiring. Inspiring the next generation. Inspiring future scientists. Inspiring everyone who looks up at the night sky and wonders, what's out there? What are we missing? What will we discover next? The future is bright, full of possibilities, full of discoveries, full of mysteries. And Webb is just getting started. The journey continues. The exploration goes on. The wonder remains. Every night, as Webb observes, it's making new discoveries, revealing new secrets, answering old questions, raising new ones. The universe is vast, it's mysterious, it's beautiful, and Webb is helping us explore it. One observation at a time, one discovery at a time, one revelation at a time. The impact of Webb extends beyond science. Its images inspire, they move, they connect us to the universe, to each other, to something bigger than ourselves. They remind us of the beauty of the cosmos, of the wonder of exploration, of the power of human curiosity. People around the world have been moved by Webb's images, have been inspired by its discoveries, have been reminded that we're part of something bigger, that the universe is vast, that mysteries await, that exploration continues. The James Webb Space Telescope is more than just a telescope. It's a symbol of what we can achieve when we dream big, when we work together, when we refuse to give up. It's proof that the impossible is possible, that the universe is waiting, that the mysteries await, and that we can discover them, one observation at a time. Tonight, as you rest, Webb is still observing, still discovering, still revealing the universe's deepest secrets, the first stars, the first galaxies, the first everything. The journey continues, the exploration goes on, the mysteries await, and Webb is our guide. I'm Sleepy, and this was your science story for today.